Hi everybody, welcome to week 13. I'm going to break this week into 2 videos as well, so let's go ahead and get started. Let's talk about the main idea of this week, and that is we want to have a kitty rodeo. So here's a video for you. See the cat? Woohoo! Yay! Okay, so the cat jumps through the hoop. Here's what we're looking for. Okay, we've got a hoop of some sort. We have a vector field, which is cats, and they could be going all over the place. Well, vectors are straight, so that shouldn't be curved. They're going all over the place, and we want to know how many cats go through the hoop. Here's our notation. I'll have a little S down here for a surface very often. Here's our notation. The vector field is the flow of the cats. Cats go all over the place. Those are my cats. The dA is the size and the orientation of the hoop in relation to the vector field, in relation to the cats. If my hoop is over here, I'm going to have different cats go through it, and I'll have a different count. But that's what I want to do, is count the number of cats that go through the hoop. Okay, so let's talk about that dA. All right, first of all, we're going to talk about just an A as a vector. What does an A as a vector mean when we have a hoop? The size of A will be the area, and the direction of A will be preset, but it must be perpendicular to our shape. Note, if A happens to be parallel to a plane in the system, this is easy to work. So let's look at an example. Here I have a triangle. We're in 3 coordinates. So here's my X, my Y, and my Z. I'm at the origin. I'm at the point 0, 3, 0. And I'm at the point 0, 0, 2. So this triangle is what I'm looking at right here. All right. And I'm giving you a direction of -I. There's my orientation right there. What is A? Well, I take the area of the triangle, 1/2 times base times height. I take a unit vector perpendicular in the orientation that I have, which this already is. I is already perpendicular to my triangle, and it's already a unit vector. So all I have to do is take 3 times my I, and there's my A as a vector. Cool? All right. Here's a homework question. Now we're going to compute the flux. So we want the total flow that goes through a certain hoop. This is the vector field, so these are the kitties. All right. And the rectangular region is the hoop. And since this is a nice, easy rectangular region, it's perpendicular to one of the planes in the surface, and I already have a direction which given to me, this is going to be actually easy to calculate. So I'm just going to take F dotted with A. So let's calculate A. To find A, I need to first find its area. It's a rectangle, and so length times height equals 1. And to make that a vector, I take a unit vector in this direction. Well, that would be K would be an easy unit vector. In fact, it's the only unit vector in that direction. And so my vector A is going to be 0, 0, 1. Because I'm taking 1 times the vector K. So there's my vector A. And then to find the flux, all I need to do is take F dotted with A. So I'm taking 3, 4, 5. There's my F. And I'm dotting it with 0, 0, 1. There's my A. And the answer is 5. Notice it's a scalar, not a vector anymore. Okay. Let's do another example. A little bit tougher. Here's my vector field. I have a rectangle where Z equals 5. So I'm up here at 5. X goes from 0 to 2. Y goes from 0 to 3. So this is 2 units, that's 3 units, and it's perfectly horizontal, which is nice, and we're oriented upward. So a unit vector in my upward direction will be k. And so let's calculate our A. A is going to be the area of my rectangle times a unit vector in my direction. So there's my A, and I want to dot that with F. X, Y, z squared plus 5, dotted with 0, 0, 6, is going to be 6z squared plus 30. All right. And let's see. Notice z is a constant equal to 5. Z is constant. If z were not constant, I couldn't do this. But since z is constant, so 25 times 6 is 150. So this is 180 for my answer. Let's go a little bit farther now. What if the f is not constant? In the previous problem, because my z was a constant, my f turned out to be a constant, at least in the coordinates that I cared about. My f turned out to be a constant. What if my s is not parallel to a plane? What if my s is not even flat? Then this is what I'm going to do. I'm going to break the xy plane up into dx and dy. So this is down on the floor, and I'm going to project these up. And when I project those up into tangent planes, I'm going to get little parallelograms. So this is the projection of a delta x, delta y rectangle tangent to the plane. That's what I'm doing there. Okay? How am I going to do that? Let's look at a side view. One thing to notice is that we learned a long time ago, if you take two vectors and cross them, so here's one vector and here's another vector. If I take the cross product of those vectors, the result of that is perpendicular to both the vectors. So it'll be perpendicular to that little tangent parallelogram, and its length is the area of the parallelogram. So that's what we need, right? That's what the A needs to be. Its length has to be the area of the shape that we've got. It needs to be perpendicular to the shape that we've got. So if I could find that U and that V, then I'm golden, right? Here's how I'm going to do it. Let's look in the X direction. If I look at a side view of this surface, so here's my Z is my vertical axis and X is my horizontal axis. So right here is my delta X right here. All right, I'm going to take that little tangent vector. That's one of these vectors along here. Its X coordinate is going to be delta X. Its Y coordinate, back from Calc 1, is the derivative times delta X. That's the differential, right? So in 3 coordinates, we're working in a 3-coordinate system, and this is just the side view. In the X direction, I'm going to have a delta X. I'll write it as a dx because you know we're going to do calculus, so we're going to take the limit as my delta X goes to 0. My height is f sub x times dx, and my y direction, that is going nowhere in the y direction. That's this vector here. In the other direction, here's my y coordinate, here's my z coordinate, and I've got the same thing going on. Nothing's going to move in the x direction because I'm starting off here parallel to the y-axis down here. Okay. In my y direction, I'm going to have a dy, and in my z direction, I'm going to have f sub y times dy, because I'm looking at the slope in the y direction. And so I need to cross these. Let's do that on the next slide. Ijk, ij, dx, 0, fx dx, dx, not fx, and 0, 0, dy, fy dy, 0, dy. And if I cross in the I direction, I'm getting a 0, and I'm getting a minus fx dx dy. For my j's, I'm getting a 0 and a minus fy dx dy. And in the k, I'm getting dx dy minus 0. This is my dA. And I can factor out a dx dy, so I'll get a minus fx minus fy 1 with a dx dy factored out. Okay, that's one possible dA. Notice the z component, the k component of this is a positive 1. So this might be slanted off to the side, but it's pointing upward. Maybe not straight up, but upward. Okay, perpendicular to the surface and upward. Sometimes we're going to have a vector that we want to point downward. This would be oriented upward. If I want this oriented down, I'm just going to take the negative of it. So that would give me a positive fx, a positive fy, and a negative 1 dx dy. And that would be oriented downward. So the problem will tell you if you want this vector to be oriented upward or oriented downward. Okay, but you'll just take what you've got and you'll look at the z component, and if it's not the correct one, then you'll just take the negative of it to get the other one. That's all you need to do. Let's look at an example. Let's set up this integral to calculate the flux. So we're calculating the surface integral of f dotted with dA. That's what flux is. All right, so there's my f is zxy. Here's my surface, 26 minus 5x plus 8y, oriented upward. So I want the positive k component. And then I have limits of integration that I'm going to work with. So I need to calculate my dA first. It's going to either be plus or minus negative fx, negative fy 1 dx dy. It's oriented upward, so I'm going to use the positive. My negative fx is negative 5. My negative fy is negative 8, getting those from my surface. 1 is just 1, so now I know my dA. This does not always come out to be constants. Because this is a plane, these are constants, but you may have variables here. Don't freak out if you do. 5, negative 8, 1 dx dy. My f is zxy, so now I can set this puppy up. zxy dotted with 5, negative 8, 1 dx dy. This is my f. All of this is my dA. And my limits of integration are from 0 to 5. Yes, x was first, so my x coordinates first. Y is on the outside, so my y on the outside. And let's do one more step before we move on. 5z minus 8x plus y dx dy from 0 to 5 and from 0 to 10. So there's my integral right there. And I know you know how to do that, so I won't take your time up in the video doing it. So we calculate our dA by the formula. Just know this. Just know it. You don't have to go through all that work every time. Just know that it's negative fx, negative fy1, and then it's either plus or minus depending on your orientation. All right. Let's look at other coordinate systems. Okay, this can get really messy, so we're only going to look at 2 specific cases in this class. And really, when it comes down to it, you're only doing these 2, you only move to these other coordinate systems because it makes your setup easier. So if you had a harder shape, you probably wouldn't even be moving to cylindrical or spherical coordinates. So that's why we're only going to look at these 2 cases. Here's my first case. If we have a cylinder and we're going to work in cylindrical coordinates, our surface has radius r, and that r is a constant because this is a cylinder, and our orientation is going to be outward from the cylinder. And in cylindrical coordinates, when I mean outward, I mean parallel to the xy plane. It doesn't have any slant to it. So horizontal, this outward, these are horizontal vectors. Okay? In that case, this is your dA. The r is a constant. Just know it. Okay? That would be a good thing to write on your note card for the exam. You do not need to memorize that. Just know what it is and how to find it. The other one is if we're in cylindrical coordinates, we're on a sphere. No, I'm say cylindrical. Spherical coordinates, sorry. We're on a sphere. The radius is r, and again, this is a constant. And we're oriented outward. Then all of this is your dA. And again, just have it on a note card. And again, the r is a constant, so you can just plug that constant in there on that sphere. Let's do one example. Let's calculate the flux of 4z00. Our surface is a sphere of radius 11. We're in the first octant, and we're oriented outward. If this were oriented inward, then I would just take the negative of what I had. But let's orient outward. Okay, so let's try this again. Sorry about that, I got fat fingers. So let's draw this guy. We're in the first quadrant only. So this is the floor. Comes down here, comes down here. Kind of looks like that, roughly. Okay, my r is equal to 11. So the first thing I need to do is change my f into spherical coordinates because I'm a sphere. If you remember that little triangle I told you, z, r, and rho, and phi, z is equal to rho cosine phi. So this vector field is going to become 4 rho cosine phi 0, 0. All right, the sphere tells us that we're in spherical coordinates. The radius tells us our r. Our first octant will tell us what our limits of integration are. We're oriented outward, and that's what we need for this. So let's set this up. I'm going to have a double integral of my 4 rho cosine phi 0, 0 dotted with sine phi cosine theta, sine phi sine theta, cosine phi times r squared, but r is a constant, sine phi d rho d phi d theta. My limits of integration, phi Whoops, not d rho. Pardon me. D phi. Phi starts at 0 and goes to pi over 2. Theta starts at 0 and goes to pi over 2. So there's my setup. What a mess. Let's see what we get. Oh, I've got one more thing. Rho's a constant, so I can put a constant in for that row. And I think those are all my rows. Okie dokie. So I've got a 44 here. So I'm going to have 44 cosine phi, sine phi, cosine theta, plus 0 plus 0, times 121 sine phi d phi d theta. So I'll pull those constants out. 121 times 44, whatever the heck that is. Need another integral there. 0 to pi over 2, 0 to pi over 2. And what are we left with? Cosine phi sine squared phi cosine theta d phi d theta. That's not too bad. I would let u be equal to sine theta, sine phi, excuse me, sine phi, and then my du will be my cosine phi d phi, and you can handle it from there. So I won't go any farther with that. All right, in the next video, we'll talk about another approach to flux. Thank you very much.